Hello, this is Jack Jackson. Today we're going to talk about midpoint and distance. So we're talking about taking a line segment. If we're given the coordinates of the endpoints, how do we find the coordinates of the midpoint? Pretty simple little formula for that we're going to go over. And then we're going to talk about the Pythagorean Theorem, one of the most famous theorems from geometry. We're going to prove that theorem, and then we're going to use that theorem to derive a distance formula, so that if we know the coordinates of 2 points, we can find the distance between those 2 points if we know the coordinates in a plane. And then we're going to do a few exercises applying this and some earlier things that we've learned about things that you can tell about 2 points and the line segment between them. So if we're given 2 points, we're going to label them like this: x1, y1 for the first point, and x2, y2 for the second point. Notice that the x's are first coordinates, y's are second coordinates. The sub 1s means it comes from point 1. The sub 2 says it comes from point 2. And we have a pretty simple little formula that should make sense to you. For the midpoint, we just simply average the x-coordinates to find the x-coordinate of the midpoint, and we average the y-coordinates to find the y-coordinate of the midpoint. So the midpoint is halfway horizontally and halfway vertically between the 2 points. Makes sense? By definition, a midpoint says that, so if we have a point x1 here, y1, our point A, and our point B, x2, y2, the midpoint is such a point such that the distance from A to M is the same as the distance from M to B, and it's between those 2 points. It's on the same line. Okay, so all 3 points are on the same line, and those distances are the same. That's what makes it a midpoint. So, we can construct a line segment AB. M is a point on that line such the distance from A to M is the same as the distance from M to B. Now make vertical and horizontal line segments coming straight down from M and straight across and straight down and straight across from A, so that we have this formed here. And so we have a right triangle formed right here, AMC and MBD. So they both have right angles here at the corner. They both have the blue sides. The hypotenuse is congruent from one to the next. And then let's look at what else we have. Well, since the 2 red sides are horizontal, they are parallel to each other, and the blue line is what we call a transversal, and it cuts that and makes these angles congruent. Similarly, the vertical sides are congruent, and corresponding angles here cut by transversal are congruent. So basically we get all the angles the same here. So either by the angle side angle or angle angle side theorem, we know that these 2 triangles are congruent. Well, if the 2 triangles are congruent, that means their corresponding parts are congruent. So the 2 red sides are congruent and the 2 green sides are congruent. Well, that tells us that this red side has to be exactly half of this distance from A to E, and the green side here has to be exactly half the distance from B to E, and so that gives us exactly what we're after. The D is the same distance from B as it is from E, so, and C is the same distance it is from A as it is from E, and so the horizontally M is halfway between A and B horizontally, or their x-coordinates, and same way for the y's. So it's pretty straightforward. In our example, we see we have the point 5,1 for the A and point 11,5 for the B. And so to find the M, halfway between 5 and 11 is 8. You can find that by 5 plus 11 is 16. Divide by 2 is get 8. And then same way for the y's, 1 plus 5 is 6. Divided by 2 is 3. And so, of course, we see the point 8,3 there is the midpoint. Pretty simple little formula. Now we're going to look at the Pythagorean Theorem. The Pythagorean Theorem is a little bit harder to prove. So we're going to look here at a geometer's sketchpad sketch that I've made for this. Now they're actually, this is a very, very famous theorem. It goes back at least as far as Pythagoras. About 900 BCE, so very old theorem. And there are many, many different proofs of this theorem. And I'm going to show you one proof that I like. So Let ABC be a triangle with sides of length A, B, and C. Then ABC is a right triangle with a right angle at C if and only if A squared plus B squared equals C squared. So all of that's needed for the Pythagorean theorem, including what's usually called a Pythagorean theorem and also its converse. So this is an if and only if, so we're going to prove this going both directions. So once we're going to assume that it is a right angle at C, and then we're going to prove that we get the relationship A squared plus B squared equals C squared. And then we're going to go backwards from that to prove the converse, to show that if A squared plus B squared equals C squared, then C has to be a right angle. And we have to do the first direction first. So here we go. So here's the proof of the first part. So let's read this, and as we read it, I'm going to click on some things that are going to make the picture go. So let ABC be a right triangle with a right angle at C, and let their sides be A, B, and C as indicated here. So the distance from B to C is A, little a. The distance from point A to point C is little b, and the distance from point A to point B is C. So the A is the blue length, B is the red length, C is the green length, and we're given that it's a right triangle, a right angle at C, so this is a right angle. So what we want to eventually show is that we get this relationship that A squared plus B squared equals C squared. And this can be any size right triangle that we want here. Okay? So let's look at that one. Okay? Now what we want to start by doing is extending line segment CA, extend this on out an additional length of B. Okay? And an additional length of A to a point D that is a length A plus B away from C. So extend that straight out. Now we're going to extend out CB a distance B out to a point E. And so now we have a right angle here from D to C to E, and the distance from D to C is A plus B, and the distance from C to E is also A plus B. So we've got ourselves basically two sides of a square. So what we're going to do next is construct some perpendicular lines here and finish our square out. So we can construct a perpendicular line D from D, perpendicular to A to DC through D, and a line perpendicular to CE through E, and call their intersection F. Okay? And it turns out, of course, those two lines will be perpendicular. And, of course, now what we have here is actually a square. So CDFE is a square, and each one of the sides has length A plus B. Okay, now what I want to do is I want to go out between D and F here. I want to find a point that's B units from D, and of course then it'll be A units from F. And then I want another one that's B units down this one from F here. So let's go ahead and construct those here. So now we find our point G is between D and F, and it's B units from D to G, and A units then from G on to F. And then it's B units from F to H, and A units from A to E. Now I'm going to connect G and A, G and H and B. Okay, and that's going to finish out our construction. Now at this point we don't know how long these lines are. We want to be able to show that they're length C. How can we maybe go about doing that? Well, do you notice we have four triangles formed now? All four of these triangles have a side of length A, a side of length B, and a right angle between them. So all four of these triangles are congruent to each other by the side angle side postulate from geometry. So those are congruent triangles. Well, since they're congruent triangles, all the corresponding parts of congruent triangles have to be congruent, not just the ones that we knew ahead of time. So we knew ahead of time, by the way we made it, that the red sides were all the same length, the blue sides were all the same length, and the right angles were all the same size. What we now know is all the green sides, the hypotenuse of each one, are all congruent. So since the first one had length C, they all have length C. So now we know that AGHB is actually a rhombus. It's a quadrilateral with all the sides the same length. Now, what about the angles in this one? Can we figure out what they are? If at least one of them is a right angle, then in fact they're all right angles and we have a square. But we don't know that yet. Let's let's manipulate it a little bit and see. It looks like remember I'm starting with the triangle, so I'm manipulating the original triangle here because I can start with any particular triangle. Well, it looks like it's going to keep being a square, but can we prove that? Well, we don't know anything about the angles yet, but wait a minute, we do know something about the angles on the triangles. Okay? So, one thing we know is the corresponding parts of all those triangles are the same. So all of these angles here that I have marked in orange are all congruent to each other. They're the angle where the red side and the green side meets. And let's call its measure T, whatever that is. Well, one thing we know about this angle right here, we know about the three angles in any triangle that their measures add up to pi radians or 180 degrees. And so we already have pi over 2 radians or 90 degrees taken up by the right angle. So that leaves pi over 2 radians or 90 degrees for these two. If this takes t, that means this one is 90 degrees minus t. Okay. Now let's look right here. From C all the way to E is a straight line. So if we took at this point B, we look around here, we must have 180 degrees or pi radians for the angle here. Well, let's think about that. That's going to be T plus whatever angle this is from A to B to H. That angle at B right there, the corner of our quadrilateral in the middle, corner of the green quadrilateral, whatever that angle is, when you add to T and you add 90 degrees minus T, you're going to get 180 degrees. Well, the minus T and the T cancel. Subtract 90 degrees from both sides, and you get that that angle there has to be 90 degrees, or pi over 2. Well, once you get one angle, the 90 degrees in a rhombus, they all have to be. One property we know of rhombus is it's a parallelogram, so opposite angles are congruent, so those are both 90 degrees. And we know that the consecutive ones are supplementary, so they add up to 180 degrees because it's a parallelogram. And so, in fact, they're all 4 right angles. So, in fact, now we have us a square here. So that area is the area of a square. So now if you look at it, we have actually our whole big square is made up of 4 parts. 5 parts. 4 of them are triangular areas, and 1 is a square area. Now each of those 4 triangle areas has an area of 1/2 times A times B. And we have 4 of those. Plus we have the area of the square, which is C square. So if we get the area of the big rectangle, big square, the square CEFD, it is these 5 areas added together. But it's also the area of a square, because the way we've got it made, that's definitely a square. And so the big square has length of side A plus B. So the area of the big square is A plus B squared. So if you look down here at the bottom, you'll see a computation. So we know that A plus B squared is the same as 4 times 1/2 A times B plus C squared. All right, let's do a little basic algebra here. 4 times 1/2 is 2, so this is 2AB plus C squared on the right. A plus b squared is a squared plus b squared plus 2ab. Use the distributive property a few times to get that, or FOIL, which is a shortcut, and you'll see long multiplication algorithm, however you want to say that, you get this multiplied out. Now subtract 2ab from both sides, and voila, we have the result, a squared plus b squared equals c squared. So notice we started with any triangle that we wanted to that was a right triangle, and we were able to prove that a squared plus b squared equals c squared. So that's the proof of the forward direction of the Pythagorean theorem. So we've shown that if the triangle is a right triangle, then a squared plus b squared equals c squared. We now want to show the converse. That is, if a squared plus b squared equals c squared, then it has to be a right triangle. So again, let's start with the triangle ABC. But this time, we don't know anything about the angles up front, but we do know this relationship that the sides have, that a squared plus b squared equals c squared. Now, let's make a new triangle, okay, triangle DEF. Now, this triangle DEF, here's what we know on it. We know that side DF is the same as the length as side AB, so those are congruent, they're length B. And we know that FE has the same length as CB, so those are both A. And this time we're going to assume that this one has a right angle. So what we don't know down here is how long the hypotenuse is. We'll just call it X. Okay? Now what we do know, however, because this one's a right angle and because the part A of our proof that we just did, the forward direction of the Pythagorean theorem, says if we know this is a right triangle with a right angle there, we have to have a squared plus b squared equals x squared. So we have a squared plus b squared equals x squared, but wait a minute, we also have a squared plus b squared equals c squared. So x squared has to be the same as c squared. But x and c are positive numbers because they're lengths, so that means that x has to be the same as c. So that tells us that those two sides, the green sides, are the same length. They're length c. So now compare triangle ABC to triangle DEF. All three pair of corresponding sides are congruent, so these are congruent triangles by the side-side-side theorem. And so all corresponding parts of triangles are congruent, so since this is a right angle at F, we must have a right angle at C, and so we prove the converse of the Pythagorean theorem that says if we have a triangle with sides of length A, B, and C, where a squared plus b squared equals c squared, then the side of the angle opposite the side of length C must be a right angle. Okay, so when we come back to the PowerPoint, this proof is going to be here. And now let's look here. The Euclidean distance formula in a plane really is nothing more than just the Pythagorean theorem. Okay? Remember, that was our goal, was to come up with the distance formula. So if we start with the point x1, y1 and another point x2, y2, then simply go over here and make a side going to the right or left and a side going up or down, so finish off a right triangle there. This side is delta x. Well, the length is the absolute value of delta x. Delta x could be positive or negative, but the length is positive, so it's the absolute value there. And the length of the vertical side is the absolute value of delta y. And the distance d, we'll call that, the length of the red side, we'll call it d. Well, by the Pythagorean theorem, the absolute value of delta x squared plus the absolute value of delta y squared equals d squared. Solving for d, we get d as the square root of absolute value of x squared plus absolute value of y squared. Now it turns out here we don't have to worry about the absolute values, because whether delta x is positive or negative, when you square it you're going to get the same thing. So we can drop the absolute values, and so here's basically our distance formula. D is the square root of delta x squared plus delta y squared. Of course, delta x, by that we mean x2 minus x1, and delta y we mean y2 minus y1. Notice that there's no shortcuts here. You first have to subtract to find delta x and delta y, then square, then add, then square root. This square and square root, for example, don't cancel. So let's put these formulas now into practice, along with some practice of some earlier formulas that we've worked with. So, given 2 points, let A be the point 23 and B be the point 47, and if possible, compute all of the following going from A to B. The midpoint of line segment AB, delta x going from A to B, delta y going from A to B, the distance from A to B, the slope between those 2 points, that is the slope of that line segment, or the slope between those 2 points. There is going to be one line there. If possible, find the point slope form of the line through A and B, centered up at A. Remember, we center up at a particular point in the point slope formula. Use also the point slope formula and form of the line, but center it at B this time. Find the y-intercept of the line through A and B, and find the slope y-intercept form of that line, or just the slope-intercept form. Find the the x-intercept of the line through A and B. Find the slope x-intercept form of the line, and then put all this on a graph. Graph this, graph the 2 points, get your straight edge out and make the line through them. Plot the midpoint, plot the x-intercept, plot the y-intercept, see the distance, make sure you can see all these things on the graph as well. So get out a piece of graph paper and plot this out, and then compute all these on there as well. When you finish that, come back and let's check your work. Alright, so we should see something like this. The point 23 says right 2 and up 3, there's the point A. The point 47, 4 on the x-axis, 7 on the y, there's point B. So the line segment we're talking about is this blue segment, light blue segment from A to B. Its midpoint is right here, which is the point 3, 5. How can we find that? Well, we take the x's and average them. So 2 plus 4 is 6, divided by 2 is 3. And we average the y's for the y-coordinate. 3 plus 7 is 10, divided by 2 is 5. And so we can work it out that way. The horizontal change is delta x. Since we're going to the right, that's going to be positive. That's x2 minus x1. 4 minus 3 is 2 to the right. We can see that visually here is just going over 2 units on our grid to the right. That's the green amount. The pink amount going up here is our vertical change. We're going up, so it should end up being positive. So 7 minus 3 is 4, so it should be 4 units up. Let's count. 1, 2, 3, 4. Sure enough, that's 4 units up. The distance from A to B we do from the Pythagorean theorem. This side, delta x is 2. This side is delta y, which is 4. So we do 2 square plus 4 square, and then square root that. So that's 4 plus 16 is 20, and then square root of that is square root of 20, or 2 times square root of 5 if you reduce the radical, approximately 4.47. And if we measure that against the scale here, lay a ruler down here and then mark it, and then measure it on either the x or y axis. Hopefully I've got a square scale here, and then you could measure it on both axes, and you'll see that makes sense for it to be about 4.47. The slope of the line is delta y over delta x, so again we use the same delta y and delta x. 4 divided by 2 is 2, so this says if we go the right one, we go up 2. That actually takes us to the midpoint. Right 1 and up 2 more gets us to B. And so from every point you go right 1 and up 2, you'll be a point on the line. So the solid line there that is dark blue, what is the equation of that? Well, point slope formula would be y equals m times parentheses x minus x1 parentheses plus y1. M is 2, x1 is 2, y1 is 3. So it's y equals 2 times x minus 2 plus 3. If we center it up at point B, we just change the 2 and 3 to 4 and 7, and we get y equals 2 times x minus 4 plus 7. To find the slope y-intercept form, just take one of these, either one, distribute and combine like terms. So we get y equals 2x, and then we got minus 4 plus 3 is negative 1. Works down here. 2x, we get minus 8 plus 7 is negative 1. So y equals 2x minus 1 is the slope y-intercept form. The program I've got these in is rounding everything to 2 decimal places, even if they're zeros. So it's showing some unnecessary zeros here, but I would just write it y equals 2x minus 1 if I was writing it out by hand. To find the x-intercept, just take this slope y-intercept form and factor out a 2, dividing both coefficients by 2. Of course, 2 divided by 2 is 1x in here, and then is 1, and then we have times the x, and we have negative 1 divided by 2 is negative 0.5, and so we get y equals 2 times x minus 0.5, so 0.5 is the x-coordinate of the x-intercept. So the x-intercept is 0.5, or 1/2, comma 0. The y-intercept is 0, negative 1, and sure enough, that bears out right here on the graph. So this brown point is the x-intercept, that's the point 1/2, 0, and the purple point down here is the y-intercept, and that's the point 0, negative 1. Okay, let's try the same thing again with another one. So here's another set of points, negative 2, negative 5, and negative 6, 3. Do exactly the same thing again. Find all these things, and then come back and check your work. Okay, now that you're back, we look at this one. This one, going from point A to point B, we're going left and down, so both delta y and delta x are negative numbers. Let's check this out. So we average the x's. Negative 2 plus negative 6 is negative 8. Divided by 2 is negative 4. So that's the x-coordinate of the midpoint. And the y-coordinate of the midpoint, we take 5 plus 3 is 8. Divided by 2 is positive 4. So negative 4, positive 4 should be the coordinates of the midpoint. And if you look, that's where we have that. Makes sense. And if you look, we have A and B plotted in the correct places. The horizontal change, just counting on the graph, it looks like I'm going left 1, 2, 3. Looks like it should be negative 4 and then negative 2 for delta y. Let's check it out. Negative 6 minus a negative 2 is negative 6 plus 2, which is negative 4 for delta x. And delta y is 3 minus 5, which is negative 2. Okay, that checks out. Find the distance between the two, the length of this lighter blue segment from A to B. It's the square root of delta x squared plus delta y squared. Since we've already figured out delta x and delta y, we just plug in. Negative 4 squared is 16. Negative 2 squared is 4. 16 plus 4 is 20. So we get square root of 20. I think that's what I got last time. So same thing again. The slope is delta y over delta x. So it's negative 2 over negative 4. The two negatives cancel. So we see we have a positive slope, which is indicated by the increasing function here. And that reduces to 1/2. So it says if we're going to the right one, we're going up 1/2. So for example, from B, right one up 1/2 is here. Right one up 1/2 gets you to the midpoint. Right one up 1/2, another one here. Right one up 1/2. Now you're up at A. So that does make sense. Okay. So to get the point slope formula centered at A, it's y equals 1/2 times x minus a negative 2, or you could just write that as x plus 2, and then plus 5. And similarly, if we center up at B, it's y equals 1/2 parentheses x minus a negative 6, close parentheses, plus 3. If you'd rather, just write that as 1/2 times x plus 6, and then plus 3. Don't forget the parentheses. If we distribute and combine like terms, we'll get it in slope y-intercept form, which allows us to find the y-intercept. Or, of course, we could just plug in x is 0 and work it out. But I'm going to go ahead and work it out here. So it's 1/2 x. And then, let's see, 5 times 2, 0.5 times 2 is 1, plus 5 is 6. And so we get 1/2 x plus 6 equals y for the slope y-intercept form, or just slope-intercept form. And so 0, 6 is the y-intercept, and sure enough, that's where it turns out to be on the graph. If we do the slope x-intercept form, take the slope y-intercept form, or the slope-intercept form, what it's usually called, factor out the 1/2, and we got the factored form of the slope x-intercept form. And so that's 1/2 times x plus 12, or x minus a negative 12. So that says negative 12 comma 0 is the x-intercept, and sure enough, that works out. Okay, a couple more examples like this. Take 2-3 and 8-3. Do the same thing with this one. Come back when you're finished. Okay? Well, this time, everything works out fine, but a couple things are a little bit different, because this one, since it has the same y coordinates, then it's real easy to find the average 3 and 3. Of course, we get 3. Averaging 2 and 8 gives us 5. So 5, 3 is the midpoint. You can see that here on the graph. But as we're going from A to B, we're only going to the right. We're not going up and down any. So the vertical change is 0. The delta y is 0. The delta x is 6. So we're going to the right 6 and not up or down any. So that means the distance should be 6. And if you use the regular distance formula, sure enough, you can see it worked out there. You do get 6. we could have saved ourselves a little work by realizing that distance was just the same as the absolute value of delta x here. The slope is delta y over delta x, so it's 0 over 6, which is 0. And of course we know that the slope of any horizontal line is going to be 0. As soon as we saw the matching y-coordinates, we know it's a horizontal line and the y-coordinates is 0. So the point slope formula is y equals 0 times x minus 2 plus 3 for the first centered at A. Centered at B, it's y equals 0 times x minus 8 plus 3. The slope y-intercept is 0 times x plus 3, or if you just simplify any of those formulas, they just work out to be y equals 3, which is the best way to write the equation. The y-intercept, of course, is 0, 3, which you can see in purple, but there is no x-intercept, so there is not going to be any slope x-intercept form at all. So this is just y equals 3. Finally, one more, 2, 7, and 2, 12. Work this one out and come back. Well, now this time it's the x-coordinates are the same, so we can still use the same midpoint formula. The distance formula still works, but this time it's delta y that's 5, and it's the delta x that's 0. And of course the x-coordinate, when you average that, is still 2, and you average 7 and 12, you get 19 halves, or 9.5. And that is the midpoint, as we see there on the graph. And so delta y, the absolute value of that, is going to be our distance, which is 5, and that the formula works out. But this time when we try to use the slope formula, we're dividing by 0, and so the slope is undefined. Of course, we knew this. When we have a vertical line, the slope is always undefined. It doesn't have a slope. So it doesn't actually have a y-axis. This line is parallel to the y-axis. So no y-intercept. So none of the point slope formulas, the slope y-intercept formula, the slope x-intercept formula, none of those work because there's no slope. And by the way, they all are y equals something, which of course any function is not going to be y equals. If it's y equals something with no y's, then it's a function. And this is not a function. So the equation of the line is just x equals 2. Now, in this previous set of exercises, we kept doing the same thing over and over again. Now, if you had to do something over and over again, and it's a routine process that has the same arithmetic basically all the time, it suggests there might be a way to automate this process. In the optional notes that are down below where we post this video, there's an introduction to writing programs for the TI-84 calculator. And there's also an example program called Linear. And this Linear program, it basically asks you to input 2 points, input the ordered pair for the 2 points, the coordinates, and then it's going to compute basically all the information that you just saw in the previous examples. So you don't have to do this work with the calculator program if you want, but if you do put this program in, you're allowed to use it on your exams, on your homework, and it's just a good introduction to how you can automate some things using the calculator. So consider this an optional part of the course, but it might be interesting for you to read that. So what should you be able to do after this? Not necessarily the calculator stuff. But what should you be able to do? You should be able to compute the midpoint of a line segment given the coordinates of its endpoints, state the Pythagorean theorem, and use it to solve for the missing side of a right triangle given the lengths of the other 2 sides, and also compute the distance between 2 points given their coordinates.